Welcome, everyone. This is our 16th session at Hackaday for quantum computing. And also 8 sessions ago, we started looking at code. We've been doing these hands-on exercises with quantum katas. So every week we have some new people joining. In case you missed previous classes, all of our recording. Am I sharing my screen? No, sorry about that. All right, that's sharing. Okay. So in case people missed previous sessions, we have all of our recording on Hackaday on the Quantum Computing Through Comics project. So every Sunday we spend 30 minutes to 1 hour discussing one concept. And I also post a new piece of comics every Sunday. So if people have already seen today's comics, we're gonna do again a little bit more about Groover's algorithm. All of the content we refer to the Q# documentation by Microsoft, and we use the samples from there and the quantum katas as well with Q# exercises. So today we would look at Groover again. Last class we spent the whole class discussing the Groover's algorithm step by step. And I will repeat that Groover's algorithm is using interference and entanglement especially interference, to help us get the answer quickly, more quickly than classical algorithm would be able to achieve in this particular application, which is searching for an item in an unordered list. For example, here, if you are looking for a book in the library, you have a huge library, so many books, you know which book you're looking for, but then you have to find where it is with the right title. Classically, if you're lucky, the first book you look at is the one that you're looking for. But if you're unlucky, you have to go through every single book, and given it is unsorted and is unlabeled, this library is very chaotic, then your last, if you're unlucky, the last book is the one that you're looking for. Groover's search puts all of the library books into the algorithm. And through the interference between all the books, the one that you're looking for will come out through constructive interference, and it will output as the one. So there's maybe some confusion that people may think that quantum computing is using parallel computing because you have qubits put in superposition, but is actually really using interference to destructively interfere the answers you don't want and constructively getting the answer you want. So there is really the interference in the algorithm that is playing the role. There's no parallel computing. And to recap, this is what Groover's algorithm involves. It has some inputs and then a bunch of H gates to put them into superposition. And then you have 2 boxes. The first one is allowing you to label the states that you're looking for with a minus sign. And then the second box is to revert it through the mean. So a reflection over the mean then would let your negative one becomes even larger. So in a way, Groover's algorithm is increasing your signal to noise. The other ones are all kind of noise, and gradually, when you iterate between these 2 boxes, the other states would decrease in amplitude. But the one you're looking for would continually to amplify its amplitude. This is really interesting algorithm, very cool that we can do something like this. And I also mentioned that Goover's algorithm scales and has a order of 2 to the n over 2, so square root of 2 to the n, as your scaling with number of qubits. Whereas classically, as I mentioned, if you have to look at every single book and using bits, that would be 2 to the n bits with for the scale. At some point, so you don't know how intrinsically one iteration would take with your algorithm, but is a factor depending on what type of computer you're using. So in this region, you may have your fastest supercomputer that's faster than your fastest quantum computer. But then at some point, Goover's algorithm is gonna take over, and the time it takes for it to look for the right answer is much lower than the time that it takes for the classical computer. So beyond certain qubit numbers, you're gonna get a speed up for a quantum computer. So this is unknown, the factors, how fast each computer, supercomputer versus quantum computer would take, but we know the scaling. And we also are not quite sure what this number of qubits will be. And we just know that it's gonna be a large number. Small number is not gonna be cost effective to use a quantum computer, and is not necessary to use one. But when it's large number, then it's more advantageous to use a quantum computer. But then in this region is a job for a lot of us, both in terms of hardware development and software development, to find, are there other things, other applications and algorithms that we can come up with that would use smaller number of qubits, yet achieve speed up compared to quantum. So this is a big unknown for all of us, and that's why we're learning that and trying to find interesting things. And a quick reminder, if you missed last class, definitely go back to it, because that's when we look at how we construct the whole Goover's algorithm step by step. But here is just reminding people that this box here is your oracle that introduces a minus sign, and this is your reflection over mean box that allows you to reflect all of your amplitude over all of their mean value. And these are two ways that you can introduce a negative sign to achieve this effect. And we tried the quantum tatas last week, which is using the bottom one. It's quite elegant because it actually doesn't need the last qubit. In this case, is our output qubit. We don't even need it in this box in order to introduce the negative sign. And that is what that box does. So here is reflection over all the zeros, and then adding all of these H gates, you would be able to reflect over the mean. So how many iterations is enough though? Depending on how big your list is, how many qubits you will need. How do we derive that 2 to the n, square root of 2 to the n order of magnitude? So it turned out that there's actually a really cool trigonometrical way to derive it. And there are numeric ways also. You can look it up, and I will also show you where to find those derivations. But this one, I especially find it elegant because it recalls several things that we have learned before, and we're really thinking about multi-dimensions. So still using our examples of 3 qubits, this are the 8 possible states that you can have in your system. But each of them is orthogonal to the other ones. So this is a complete set of the states in your system, and each of them, between each of them, they are orthogonal. So then you can think, because we can't really visualize more than 3 dimensions, but you can still imagine if we project it down to 2 dimension, and if we want to draw it, we would draw a 2 axis that's orthogonal, that's perpendicular to each other. So say that this one, state B, is our all 0 state. In this case, we only have 3 zeros. So I'm just writing the general case here. So if you have even bigger, larger dimension, it's got n number of zeros there. And this other state that you want to get to, in this case is 101, is this perpendicular one. And now, what you do in the first box when you reflect over your 0 axis is this here. So if you have a arbitrary state, if you have all the 0 states and you apply H gates to them, you will put them in superposition in equal amplitudes. And then your first box is to put a reflection over 0, and then you get this state. And then we know the next box I showed earlier is reflection over mean. So when you reflect over 0 for that particular state, you give it a mark, you label it, so only this one is negative. But then next step is reflection over mean. You will get to this phi dash state. There's also proof, if you want to be very, very rigorous, there's proof that when you reflect your state over 2 arbitrary lines on your coordinates, if the angle between the 2 lines is theta, then your end state will be 2 thetas away from your original one. But you can also see that, of course, this one is the mean because it's equal angle spreading out. So this is your mean axis that you are reflecting over and get to this phi dash. And if you want to write out what the states are, for example, when you're just starting with the phi state, you can write out it's got some angle theta, and it's projected to B, so it's cosine theta, and projected to A is sine theta. Now when you have a phi dash, you get cosine 2 theta projected onto B, and 2 theta projected onto A. But now if you have run this iteration k times, then it will become 2k plus 1 theta. So you have just check this, that when k is 0, you have 2 theta. You have theta. But then if k is 1, you have 3 thetas away from here, from this here. So then this is your arbitrary state after k times of iterations. You know that eventually you want to do this reflection over this one, and this one, this one, and this one. So gradually you are folding and folding and folding, and your state would eventually be very, very close to A here. And that's what Gruber's algorithm does, is starting with a state, but then moving it towards the answer that you want. So if then your end state is close to A, that means your amplitude here needs to be close to A, and your amplitude here is close to 0. So if you write sine 2k plus 1 times theta equal to 1, then you will get this pi over 4 theta minus half is your number of iterations. That's how you can prove it. I think is a very, very cool, elegant way to prove what's the number of k. And that is given us, okay, now what is theta? Theta you can find out from over here. When you get started with 2 to the n is the number of states, and n is the number of qubits. So your amplitude when you start with is always 1 over square root of 2 to the n. So that's why this sine theta a is here, because we know a will be 101, and we know its amplitude right here is 1 over 8. And 1 over 8 expanding to the general case is 1 over 2 to the n. So we already know theta right here. You just plug it in and you see actually it will be on the order of 2 to the n for k. And there's also an approximation here when the angle gets really large, then sine theta is the same as theta. So sine theta when n is very large is very close to 1 over 2 to the n. So that's why theta will be very close to 1 to the n. Yeah, so there's this kind of proof here, which is really cool. So let's take a look at the code now if we want to just try a little bit of practice. So we're not using the katas today, but we will be using the samples from the documentation page. For people who haven't seen this before, this is the Microsoft quantum documentation. And in this tutorials page, you can even find quite a few getting started samples. And we have the implement Groover search algorithm here. And it does a little bit of explanation and then goes to the code. You can copy and paste the code to your IDE, but you can also go to the Q# sample, where you can also find a GitHub repository of the exact code and download it or clone it from the sample code repository. Also, a few words about how to use this. I am going to use the Visual Studio Code. We used this previously also. It's kind of my favorite environment for Q#. And you have other options. If you don't have this installed, don't worry, I will just show you how this works. And in the quick starts, you will be able to find all about the different types of IDEs and which one to install. And we have all these different options. So I'm just using the command line, and I had to install Visual Studio Code and the QDK extension. So you just follow this if you want to do the same. So I already downloaded the sample, and let's take a look at the code here. Okay, so it comes with 2 files. The program.qs is the one that we will execute and is the main file here, but then the reflection.qs has the definition of all these gates and steps. So it's kind of written the same algorithm that we tried last week in a more concise way, in a way, because last week we were building Groover as a katas exercise, but now we want to run Groover's algorithm and also figure out the state that it would return. So here we just have an arbitrary array of qubits, and then we have something called prepare uniform qubits. So if we look at this here, or rather this one is easier. We want to prepare them, and then we do a reflection over the marked, which is this oracle here, and then do a reflection about uniform. What is uniform? I think it's just a naming thing. So we're going to look at that later. But in effect, is just doing the reflection over mean. And then it also does the calculation of the number of iterations, and is automatically taking into account here, depending on how many qubits you ask this algorithm to calculate, this would get updated. So look here, this is what we just derived, is the angular presentation here, pi over 4 theta. Theta is the angle minus half. So in this reflection.qs, we can see what these definitions are. The reflect about marked, this algorithm, this oracle here, is asking to do the x for the output qubit and the h for the output qubit. So this initializes the output qubit, this here. And the reason for doing this, as we've seen before, is to introduce that minus sign to our system so that it can be entangled with the other qubits and then label the one you want. And here is something you can modify. It's for the oracle. So I think when the sample first came in, it was 2. I changed it to 3 for fun. And when you put input qubits with the 2 as your sequence, then is the 0, 1, 0, 1, 0, 1 state. This is where you define which state in your system you want to label. And now it asks us to do the withing. Remember, we learned this in the katas. So within this, do the controlled X here. This is your controlled X. So this whole chunk is setting up the first oracle. Then there's the reflect about uniform, and it has several more definitions below. Reflect over about, I think about over maybe the same thing. Reflect about uniform here is doing a adjoint prepare uniform. So is preparing the input qubits. And what is prepare uniform is basically, again, applying all the H gates to all the input qubits. And then prepare all ones. So the all ones is defined here. Because you have to have them to be all ones in order to have this or this useful. Because when you have a 0, it's not gonna do any control on this qubit here. So this is what they call reflect, prepare all ones. So in effect, you're having all of them having the superposition, and then all the ones would have the control effect on that last qubit. Yeah, and then that's it. That's actually how you would set up everything. Here is the reflect about all ones, which is this step. And remember last time we learned about most, which is all of them, but the last one, and the tail. Tail is the last qubit. And note, these are all input qubits. We're not using the output qubit at the bottom in this box at all. So yeah, so this is how you set it up, and let's run it. In this case, so the instruction on documentation shows that you need to build the program if it's the first time you're running it, but I've already done these. So now I just need to put in the command to have it run. But it also tells you that if you do this, it's not gonna run because you haven't told the program how many qubits you have. So if we do this, let's run 5 qubits. That's what it asks. It's just an example. It's any arbitrary number. So this algorithm is built on no restrictions of the number of qubits. Kind of taking a while. Okay. Yep. So it now outputs 0, 1, 0, 1, 0, 1. That's what we defined. That's what we labeled. And you only needed to do this iteration 4 times when you have 5 qubits. But then if you have more qubits, and just for the sake of generality, I can change this here to the number and change also, let's try 11 qubits. Now, yeah, that's what it finds. It finds the correct state, and also it calculates the number of iterations that it needs to run the algorithm. Yeah, so that's how you do it on Q# in the sample. And tutorials, yeah, that's what we just did. And the katas we looked at last time, but I also want to point you to some further reading through these katas. So the Gruber's algorithm, we already did the exercise. But in here, it links to some reading materials. Of course, Wikipedia has a page, but there are some lectures. One of them uses the angular derivation, and the other ones use the numerical way. So these are all very good lecture materials if you want to study further. And yeah, these are more mathematical if you prefer. So this one uses similar. This is the proof for the 2 theta. Yeah, just read those in your spare time. And there's one more thing I want to show. Here is a really cool animation of Grubers. I have to wait for it to load. Not sure why it's not loading, but you should go to this link through the katas. Let me also see if I can copy and paste here. It's got a really nice animation, and it's got a fixed number of, it's also using 3 qubits, and then but then they have also a output qubit. So exactly like what we set up here. It's got 3 qubits and then 1 output as your the state that can introduce your negative sign. And then when you run it, it has the phase arrows showing how large the amplitudes are and how they can cancel each other out and enhance the one that you want. It's a shame, why is it not running? But I'll post the link. You can try it on your own computer. So that's it for today. It's pretty quick It's a short class today, and frequently asked question is where is this recorded? Yes, and these are the two places, YouTube and Hackaday, that you can find the recording. And definitely, if you haven't gone through the Groover's algorithm, go back to the recording for that. Also, next weekend, next Sunday, we have special classes, so I won't be teaching a class like this, not at the normal time. So we have on Thursday a female tech leaders event at this time. This is on Thursday, so if you're interested, I think you can register and listen in. But on Sunday, I will be given a workshop for the teens in AI. And it will be a summary and a revision for if you've been coming to this class, then the material is not new to you, but it's for teenagers, and I will be showing a lot of the overviews and do some exercise there. And the time is earlier than this time, so I won't be giving a class again during this time next week. And I don't think this one is open to public, so I will ask the organizer to record it, and if I can post it, I will post it on Hackaday. I will post a link there. So if you want to join this one's open. This one, I can try to get the recording for you guys. And yeah, that's it. And today is short. Next week, remember, don't dial in at this time because we're doing extra things. Okay, thanks everyone. Let me see if there's any question here. Yeah, sorry about the small screen, but hopefully it was resolved. You have to press Ctrl+ to zoom in. Okay. Thank you so much. Have a good week.